Okay, this is Alan again, continuing my series of videos on the HPCC architecture and in particular ECL. I'm doing a short series here on distributed data and how to actually use distributed data, in other words, work with HPCC. So in a previous video I've explained distributed, and in this video I'll show how to actually use the distributed nature of HPCC. So here we have a file full of people information. It's only a gigabyte in size, so it won't things run quickly, as it were, but it's big enough to demo, and it's all nicely distributed. It's a 3-node 4 cluster, this one, so you've got with replication on, so you can see there's duplication of data across different nodes. And let's just see if we can mine some data from this. So turning without further ado to ECL, first I thought I'd show how not to use HPCC. This is just a global probe of that file, so not using distributed at all. And this is what you shouldn't really be doing, because this is a kind of area you'll get skew errors, and it will take a long time as well. So here I've got a that data set defined. I've just made sure I've got some valid birth dates, and in all these exercises I thought I'd just get count of females, count of males, and the sum of their ages. Not particularly interesting, but it's a trading video. And what do I do? Well, basically I just generate a row counting the rows for that data set, and also aggregating the ages there, and I'm just passing two data sets, one filtered for females, one filtered for males, and generating a data set from those two rows using the ampersand sign here, and using the global processing. And this may be a bit small, so I'll just show the results a bit bigger. I've got this earlier here so you can actually see this, and we can compare this with other work units later on that do use local processing. Right, so that's what not to do. Now let's move on to some processing. Now this is doing exactly the same work, but really, because this local qualifier has been supplied to the table command, this table command will execute independently on each node locally. So each computer will be doing its own thing, doing its own calculations on each node independently. Same input, same results, outputs. Now if we look at the results, we can see it's a bit small, but I think you just need to see that really there are 6 results, because it's a 3-node 4, as I said, and there's 2 results per node. So this is really the intermediate results. So the heavy lifting's been done by this phase, but obviously we've a further phase to go, which is to amalgamate this information into a final result. So to do that, all we need to do is to group, roll up. I've done it by grouping, I've grouped by gender, and then just done the final aggregation with this roll up group command here. And again, you can see that the results are absolutely identical to, if I bring that up there, you might be able to see 3831709. Yeah, the results are identical to the global processing, but this won't suffer from any skew problems with skew, and it will be an order of magnitude faster than the first operation, because really all the work's been done locally. So that's table and roll up, and I've required 2 built-ins to do that, the table followed by a roll up of the intermediate results. Now you can all do that in a one-stop shop using aggregates, and this does what that previous operation has done, but so using a transform instead of a layout. So here where we have a table command, In the aggregate, we use the first transform is the heavy lifting one, and that uses a transform. And in this, the gender, the grouping, is defined by a parameter to aggregate, and you don't need to distribute beforehand on this, which is another nice point to make out, but it will still run locally. Local in this context means stop early, complete, don't do the final phase, just generate the intermediate results. So looking at this result here, you'll find again we've got these same 6 results from the 3 nodes because we terminated the aggregate early using this local command here, but the actual values are the same as for the table command we did here. Now all we have to do to make this run globally to get the final results is to remove the oh gosh, what's gone wrong here? I think I've let's just get rid of some of this here. All we have to do is remove the local command, and this means right, continue on and generate the final results here, which again, if I compare with my zoomed copy, hopefully you can see that they are exactly the same, sorted differently, but the values are identical here. Some points to note, that the merge transform aggregate has been able to deduce the merge operation from the functionality of the first transform. You can specify your own, as I had here, you can specify your own merge transform, which takes a write 1 and write 2, but I've never found a need to. The compiler seems to do a pretty good job on working out how to merge given the first transform here. And effectively the merge transform, the second phase, is effectively an iterate. It presents the merge transform with the first 2 intermediate results, so that one for females, and then the result of that merge is then passed into a second iteration, which will sum in and aggregate the next row for females, and the same for the different group for males here. And so in fact there'll be the merge operation in this particular case, because there's 3 nodes, will be 2, because it'll be 1 less than the actual number of nodes you're doing here. If you don't know what to do, one thing I just want to show, which is handy, given you've got this left and right, you want to know, find out for yourself which side takes the previous results, then what you need to do is, I do something like this, is I generate a transform, merge phase transform, which just increments the length on the result of self. So in other words, here I've got a calls, which is a string, and the first time round calls will be empty because of the result from the first transform. And you can see that I gradually accumulate in this string information from every iteration. So as it's being appended, for example, length of calls, I put a different value in here. So the results for this, you can see it's been called twice, F1 and F2. So I've put the first call, it's that's empty, gender, let's say, will be F, and the length of the current calls will be 0, so that will be 1. The second time round you'll have the original F1, you'll then have F again, and this time the length of calls will be 2, which means we put 2 in there, so you'll end up with F1, F2 as you see there. This means that it's the right hand side, which I'm presenting as left here, is what holds the intermediate results. if you try the right hand side, so I do exactly the same, but trying to use right to accumulate, you find it doesn't accumulate and just puts the current result for the current iteration in calls. So the previous result is, in this case, is not, we have proved that the previous result from the previous iteration has not been passed in at right to, but we know from this call that in fact it's been passed in by right one. I thought that's a handy little thing if you want to get your head round with what left and right is doing, is to do something like that little test there yourself. So that's it. So you've got global processing, you've got local processing, which is fast using two built-ins, but in fact you can do the same fast processing using a single aggregate function, which runs does the heavy lifting locally and then just merges the final intermediate results into final results all in one built-in. Anyway, I hope that's demystified aggregate for you, and see you in the next video. Cheers, bye.